shared connectivity for safer shared space facilities. It's about improving mobility for non-motorized and vulnerable road users. So this is how the flow of the presentation will be. It will be about, there will be a short introduction, then what is the methodology of our project, and then I will cover the task summary and then project contribution and impacts. So context of the research. The UN estimate that by 2050, 70% of the world population will be living in urban areas. And therefore, urbanization will throw challenges in terms of traffic congestion, road safety, mobility, and environmental and health issues. And obviously, because of, like we can see, there's a lot of vehicles which are being used in present times. So physical inactivity has caused about 3.2 million deaths per year worldwide. What is shared space? So because of physical inactivity, there's a lot of health hazards. So in future, we can see, or we will be seeing like the shared space, a concept of shared space will be promoted, which is about using the non-motorized transportation and also a holistic redesign of the existing mobility infrastructure. This is all about shared space, in which there will be more urban traffic scenarios, lot of non-motorized transportation like cycling, biking, e-scooters, e-bikes, all will be used, and there will be better mobility infrastructure which can help all these non-motorized vehicles to have a efficient transportation and flow of traffic. So therefore, our research focus on modeling urban active mobility and improving connectivity and shared space. Research gaps. So if we see basically our research focus on urban mobility. So what are the gaps which motivates us to work on this area? Is that a lot of existing pedestrian traffic models, they do not include pedestrian behavior. And also how the pedestrian behaves in the environment and with other non-motorized agents and vehicles. So, and also like pedestrian have their peculiar gait parameters like their step length and step frequency. So if we see the existing work, there is not much work which has included gait parameters in the mobility models. Most of the models are location specific, and also the models are agent specific also, like they cannot be extended to other traffic agents, other non-motorized traffic agents. And this, the other part which we are working on in our project is about having an efficient communication between the agents. So we will be studying about routing protocols, the MANET routing protocols, and how they can, how the routing protocols can have a stable communication throughout the traffic scenario. So project objective. So we are developing a behavior-based traffic pedestrian trajectory planning model. We are improving the communication routing protocol to ensure a stable MANET, and we apply a developed model for a various shared space scenario. The proposed framework. So as I have mentioned, our project is based on proposing a mobility model and improving the communication between agents. So first part of the project is about developing a pedestrian trajectory planning framework, which is using convex optimization. The second part of the project is about improving existing routing protocol for enhancing the communication between agents. The outcome of the project will be a stable communication channel in MANET comprising of active mobility traffic agents. What will be the implication of the project? It's like the first part, which is a trajectory planning algorithm. It's a generic trajectory planning algorithm for active mobility agent, and the routing protocol will help us to establish a stable communication, which will overall aid in analyzing safety measures as well as helpful in infrastructure design. Planning of the project. We divided our project into various phases. First phase is about development of predictive trajectory generation model. The second is building an adaptive routing MANET protocol. There are a lot of subtasks to enhance our models. And then the final phase is about coupling the phase 1 and phase 2 so that there will be a proper framework for studying various shared space scenarios. And the application is applying to shared space scenarios to improve safety and infrastructure design. Phase 1, pedestrian trajectory modeling. So this is the whole methodology for developing a convex optimization based trajectory planning. Our model has like a proper functioning, and because it has used the behavior rules and the interaction rules in the cost function. And then our model is also a predictive model, like every time step will be predicted. And for this, we have used receding horizon control. The software used for implementing of our methodology of the phase 1 is MATLAB and CVX. We have performed 3 case studies to calibrate and validate our model. So as you see from the figure, like there is a main box which shows like there is a one function, like when we are developing an algorithm, we have divided our algorithm in 2 functions. One function is about based on convex optimization and mixed integer linear programming. The cost function and the constraint will be implemented in that function, MATLAB function. And there's another MATLAB function which will be executing the receding horizon control, and that is for the predictive modeling. And the both functions are coupled, so they will transfer information of every time step between each other so that the trajectories which are generated, they are efficient and they have included the behavior and the interaction rule of the scenario. So the first function will be the cost function, which will be based on behavior rules. We have defined, like assigned the destination, the origin and the destination from the agent. And then obviously because our cost function is based on the minimization of the cost. So will be how we have defined the cost function will be based on the minimization of the variables and the parameters in the cost function. The constraints will define, like say for example, if there's obstacle avoidance scenarios and how the algorithm will avoid the obstacle, that will be defined in the constraint. And obviously various parameters like the speed and the acceleration will be defined in the constraint. Receding horizon, as our algorithm is also predictive based, so it is about like the planning horizon. If we think about an agent, a pedestrian, it plans for a movement, it plans its trajectory for a certain period of time, but actually it moves for a certain period. So that is divided into, like, planning will be the how much agent plans, and the control horizon, which like actually how much a pedestrian moves. So now directly going to the case study. So this is the photos from the images from the real data set which we have considered. So the case studies, the 3 case studies are 2 agents walking together, 3 agents walking together, and obstacle avoidance. So we have taken 40 samples, 30 were used for the calibration and 10 were used for the validation. This is the cost function which is used in the convex optimization to generate the trajectory, and it has included the behavior rules, like how much agent have a space between each other in the x and y axis, and how they interact with the surroundings, like how much distance they have with the other agent and the scenarios, and the times, like the step length and step frequency. Then we calibrated our values, like x separation is how much one agent has a separation between with the other agent, and how much in the y-axis the separation. Then the number of frames is from the data set. Then minimum velocity, all is calibrated using the data set. And we have the case 1, these are the results. So the The yellow one and the green one are the actual trajectory for the agent 1 and agent 2, and the blue and the red are the generated trajectory for the agent 1 and agent 2 respectively. This is the, like, if we consider data set, so it's for the pair 94 and 95, and same for 101 and 102. So we got, like, our model worked pretty good, like it generates trajectory with very less error, which we can see, when we have considered our performance metrics, like MED means like mean Euclidean distance for agent 1 and mean Euclidean distance for agent 2. Same for FDE is like the final displacement error from the final point. And for the agent 2, root mean square error, X separation, like how much X separation agent 1 there is between the two agents, and the Y separation between the two agents, that is the error value. So these are pretty low. So it's close to 0. So our, as we also can visually see from this graphs also, the errors are very low. Now jumping to the case study 2, which is about 3 agents working together. So the images from the real data set, we can see like 3 agents are working together. For this, we took 30 samples, 23 were used for calibration and 7 was used for validation. This is the objective function for the case study 2, and like how we have imagined, what is the case study. So this is the X separation between agent 1 and 2, X separation between agent 2 and 3, 1 and 3. Imagine like 1 is in the center. And generally, if we go back to the existing research, it says like when 3 agents work together, they form a V, which can be like a V or an inverted V, like the agent 1, the center agent will be either left behind or is leading. So based on this, we have performed the study. And these are the graphs with, or the trajectories which are generated by our model. So the purple, the green, and the blue, the teal color shows the real trajectory of agent 1, 2, and 3, and the ground truth. And the blue, red, and brown shows the generated trajectory. These are the few samples. And if we go to this result, so mean Euclidean distance of the 3 agents, then final displacement error of the 3 agent, and root mean square error between the agent 1 and 2 in the X and Y axis, and between agent 2 and 3 in the X and Y axis. So case study 3. This is about obstacle avoidance, like how an agent avoid an obstacle. Like there's a stationary car which is standing. So in this project, we have performed a stationary obstacle avoidance. So for this, we considered 20 samples. 15 were used for calibration, 5 for validation. And going ahead with the results. So this is how the scenario, and like when we are constructing our function algorithm, so we have considered a buffer zone around the obstacle, and based on the buffer zone, when the trajectories are generated, so the model consider like have a certain distance with the obstacle and then generate the trajectory. So the buffer zone is like 0.55 meter. And these are the calibrated values from the model, and these are the samples of the, so the yellow is the obstacle and the purple color shows the buffer zone. This is the summary. The values are pretty good. Now going to the jumping to the phase 2, which is about mobility aware adaptive routing protocol. So what is basically routing strategy? So routing strategy is like how the path is being defined between the two nodes, then for the transfer of the packets or transfer of the information. So basically, like we are considering MANET. So MANET, like mobile ad hoc networks. So for this, the routing protocols can be defined basically, like broadly, they can be defined into 3 categories, that is reactive, proactive, and hybrid protocol. And as there's a paper, a very famous paper in which everyone can go ahead and see, it's a beautiful paper which broadly defines how the three categories of routing protocol. And the considering the quality of service of requirement for the multimedia application. So there is another category which is quality of service routing protocol, and these protocols are based on link stability, which is about maintaining the stability and durability of paths. Basically, we are more more interested in how the link stability is maintained between the nodes, so that there is always a stable communication between the agents in a network. So there's another paper which talks a lot about the link stability and designates the lifetime, like how can we define a lifetime of a link between two nodes. And basically there are two, like either we define the distance between the nodes to define the link stability, or as a mobility of the nodes as a metric to define the link stability. Broadly, the link stability based routing protocol, like we can categorize in two more further categories based on node distance or in the nodes mobility. And nodes mobility can be further defined into nodes mobility parameters and probabilistic method. Going more into link stability, as we wanted to work towards, we are working towards link stability. So there can be distance-based routing protocol, and the famous being TDSE protocol and SSOD protocol, in which the node distance is calculated from their neighbors, and also the so like basically how like say for example, when protocol is defined, so how much distance should be, minimum distance should be there, so that there can be transfer of packets between the two nodes. And if the distance increases, then what a node should do, so that there's always a path between the two nodes. And probabilistic based protocol, it basically find the most stable node, which is mostly connected with other nodes, maybe called as relay node or something, multi-point relay node, and how it maintains, and first of all recognizing the multi-point relay, and then how the communication can be maintained between the node. So what we want to do in our work is, like, say for example, this is a network and there's a source node, and it want to transfer the information to the D node. Now the node is like there's a continuous path between the at time 1 second, there's a continuous path between up to the D node, but at time 3 seconds, say for example, D node starts moving away from the communication range of the B node, then the path will break and D node will be out of the communication range. Then what should be done so that D node remains in the communication range? So say for example, the communication range of the B node should be increased immediately, or some other thing should be done, or different paths should be found from a source node to D node to always have a communication between D node. Why we have imagined this scenario? Say for example, consider an emergency situation in which there is an emergency situation of evacuation. So like a futuristic scenario in which we want to evacuate everyone safely. So and there's a message being transferred. So we want everyone to have received the message, like there is a certain gate and everyone has to exit from a certain gate. So how all the nodes, all the people present in an evacuation area should always receiving the emergency information which is being transmitted by the units which are trying to evacuate the place. So this is how the route, so we are imagining that scenario, and then we want to improve existing routing protocol. For this, we have performed a preliminary simulation study. Like we have shortlisted certain routing protocol based on different broadly classified routing protocol categories, like AODV, DSDV, OLSR routing protocol. And for this, the performance metric, we have considered end-to-end delay, throughput, and packet delivery ratio. For performing the simulation, we have considered that MANET as a software to simulate the node scenario, the network scenario. And the simulation study will be like there will be two hosts communicating wirelessly, like different steps are being performed. between like step 2 will be adding more, like step by step. We first started experimenting, like there are 2 hosts which are communicating, then adding more nets, then setting up a static routing, then including more dynamic routing from each category like AODV, DSDV, OLSR. And then inputting the real trajectory in the software was a big challenge. Then we have this scenario in which the nodes are moving based on the real trajectory. And we have a short video also. So it shows like that to like host, it has a source host and a host destination. And as you can see, right now there's no packet transfer, and suddenly the packet transfer is maintained between the 2 agents. So there was a break for a certain period of time where there was no packet transfer between, or information transfer between host source and host destination. So this was the thing which we can call as a research gap, that there should always be a continuous information transfer between the 2 nodes. So why there is a break? So based on this, and then based on the simulation study we performed, these are the 3 performance metrics. Throughput, which is about a measure how well the network can constantly provide data to the destination. Packet delivery ratio of the number of data packets delivered to the destination node and the number of packets data packets sent by the source node. And end-to-end delay, like time taken for a packet to be transmitted across the network from the source to destination. This is a summary, like we have performed for the 3 nodes. 3 routing protocols, sorry. And then on all the study, we can see the OLSR is a pretty good protocol, managed routing protocol, which has low end-to-end delay, which should be low, high throughput, and high packet delivery ratio, and for different number of nodes between the source and source for host source and the host destination. Now the summary, task summary for the project. The phase 1 of the project is we have developed a pedestrian behavior trajectory planning model. We have performed case studies for 2 agents walking together, 3 agents walking together, and agents obstacle avoidance maneuvering. The result demonstrated that generated trajectories are quite realistic, and we are in a process of writing 1 journal paper based on the accomplished research. Phase 2 of the research, we did thorough literature review, and we have performed a preliminary simulation study analyzing the managed routing protocol. Phase 3 will be about like coupling the phase 1 and phase 2 to develop a mobility aware adaptive routing protocol. This is on which we are still working, the phase 3 of the project. And what are the project contribution and impact? So to address the near future transportation challenges in shared space, and a reliable and efficient pedestrian trajectory framework will allow us to test shared space traffic scenarios, and a managed routing protocol for a highly dynamic network like traffic network, which is a necessity, and a protocol which ensures stable communication among mobile nodes is also a necessity. So like coupling the 2 phases and then improving existing protocol will be our aim. And then our research gives upper hand to traffic enforcement agencies in handling shared space traffic challenges and provide a better traffic safety. Thank you.
Great, thank you, Saumya.
Okay.
We will open it up for any questions. We don't have any currently, but if any attendees do have any questions, feel free to type those in the chat box. And I will remind everyone that this presentation will be available on our YouTube channel and website within the next couple of days, and we'll share that link with all the registrants. So if you receive that, feel free to share that with any colleagues that may be interested. And I know, oh, go ahead.
No, I can ask a question. I'm working with Saumya, but so Saumya, where are we going with that? You mentioned at the beginning this type of modeling for pedestrian can be expanded to other road users like cyclists, scooter. How can you do that, and how to make sure It's a big claim saying that one model can be just used for other models. Can you elaborate on that, please?
Yes. Yes. It's just the advantage of convex optimization. First of all, like the way the convex optimization can be expanded to different agents and different scenarios. This is first advantage. That's why we have chosen like convex optimization for developing the model. Second, because our model is based on very less number of parameters. So like say for example, we want to use bicycle scenario, bicycle agents. So it's just like we have to define the dynamic, the bicycle, the mobility dynamic of a bicycle, and their behavior rules in our model, and our model can be expanded to bicycle scenarios and bicycle shared space scenarios. So first of like basically keeping the expansion of our model, we have this in our mind. That's why when we were thinking of designing the algorithm, we choose convex optimization and frame the algorithm in such a way that it can be expanded in future for different non-motorized vehicles.
Great.
Already the convex optimization is very too much famous for space research, the space satellites and drones and robotic, like robots movement and everything. So it's already well established algorithm. It is never being used for pedestrian mobility. So we have like introducing convex optimization to in pedestrian mobility research, basically.
Awesome. That is interesting. And were you able to see this question come in the chat box then too? How is using this way of modeling different than using machine learning models, for example?
Yes, this question, yes. So if we just go ahead, what is machine learning models? So machine learning models, first of all, the first most very big thing is like, which is said like they are like black box. So whatever being inside machine learning models, we put the data inside, we get the output. We don't know how it's being done, and we cannot manipulate or not manipulate. We cannot play with the variables inside very much. In our model, it's a cost function. So whatever, how the way we want to maximize or minimize the scenario, whatever objective we want from the call. Like say, for example, if we want a minimum time trajectory from a source to destination, we can frame the cost function that way, like an agent walks from a source to the final destination in a minimum time. So we can play with that. If we want some other things, say for example, with the maximum speed, I'm just guessing, like we define like agent has to walk with such a speed. So we can play with such constraint in the algorithm. But with my understanding, whatever understanding I have for the machine learning models, we cannot do that. Like we cannot play as much we can play in convex optimization. Secondly, with this convex optimization, it's not too much dependent on the data. We don't need a lot of data to calibrate our models, the variables and the parameters of our models. As such, like machine models are dependent on data because they learn from the data itself. So it's not, this model is not learning, we are just calibrating the model. We are not learning, our models are not learning from the data basically. So this is the two basic difference, and if we dig more, we can find more. Because it's a more of optimization. So optimization is a different field of study.
Great.
Thank you.
Well, I think, oh, hey, another question came in. What is the data you used for your model?
Oh, it's a data based on a university in China, and it's collected, shared by an Ohio University student. It's an old data set. If you want, I can share in future with in the link on in the chat. So it's data which is available on GitHub. So like finding that data for the shared space, what a tricky thing, because we want to expand our model for different scenarios. So we want to have a data set which is more in a sense of a shared space, which has obstacles also, which has pedestrian moving with no traffic light, because shared space will be more about blurring the segregation of the modes and less of traffic and rules. And then also the agents are moving safely. This is all about shared space, like communicating and moving safely with less of rules. So so we looked for the data, and like it took time, but we finally got a good data set. So I can share in the chat when it's required.
Awesome. And I was going to say, you know, we will send this recording out. I'll include your email, Saumya, in that email to the registrants, so they can reach out to you and Professor Zaki if they do have any follow-up questions or comments. But I know we are a couple minutes over our time, so I do want to thank everyone again for attending, and thank Saumya for the presentation. This was great. So with that, I think we'll end it there. Keep an eye out for announcements for our next webinar, which will be coming up in October. All right.
Yeah.
Thank you.
Thank you. Thank you.
Thanks, Jacob.
Thank you everyone for listening and participating. Have a good day.
Goodbye.